welcome to this morning session. Welcome, since all of you have time to come on a Sunday morning here. There are few things you never anticipate you will do with life. This is one such thing. I never anticipated that I have to give a talk on memory of Professor Amit Dutta here. It's impossible to summarize anybody's research career, even if for a few years, in a matter of 30 minutes. Summarizing 30 years of work in 30 minutes is next to impossible. So what I'm going to do essentially is to just motivate some sort of questions. The questions he was asking in his research and the kind of problems he was trying to solve. So that's essentially what I will try to do, give you a flavor of such questions. Amit, as Amit Dutta we would call, spent a significant amount of time in these three major places. Calcutta, where he did his PhD in SIIT. Then he went for a postdoc to Germany, in Dresden. He spent some time in Würzburg. And then he spent most of his adult career in Kanpur. And as he was aging gracefully, he, as we know, as a charismatic theorist, he was traveling through a set of ideas in physics, and this talk will be an attempt to give you glimpses of them. Before we start, I have to motivate what is charismatic physics. Okay? And charismatic physics is the idea of thinking about emergent phenomena. For instance, if you look at an evening sky where there is a flock of birds moving around, we may understand how a single bird moves. Even that is quite difficult, but we may still understand how a single bird moves. But when you look at a pattern of birds, the fact they decide to stay in some distance from each other, the fact that they make a pattern, the fact that they try to behave in a particular dynamical structure, this is the idea of charismatic physics. The idea that there is an emergent phenomena coming out of basic constituents. Or, for example, the piece of glass from which I am seeing through is, although as a material it's silicon oxide, something which we all understand, but the fact that glass is transparent, that it shines, that it conducts heat very well, is an emergent phenomena coming out of this structure of silicon oxide. So while we may understand every constituent which forms these materials, it is this, when they come together, when these constituents come together, they behave in very different ways. Another very simple example all of us have seen is that of carbon. The carbon picture of carbon element is this, how it looks. It has 4 valence electrons. But when arranged in a crystal structure, it forms the diamond. When arranged in a hexagonal pattern, it forms the graphene, which is part of your pencil lead. Since it is a layered compound, it can easily be put onto paper. It shines and is black in color. That's why you can see it when it is written on paper. When wood is burned, you see carbon as a form of an amorphous compound, which is just very sooty in nature. So this is essentially different phases of carbon. A charismatic person, in particular a theorist, what a person is trying to do is to write minimal models, the simplest toy model you can create in order to show the simplest phenomena. For instance, all these different materials are now understood in terms of various kinds of ways of arranging carbon atoms. Is there something new you can write? Is there another way of arranging carbon atoms, another bit of information you can put which will demonstrate a new phenomenon? Okay, and this is what any quantum theorist in general is trying to do. And Amit Dutta was a fantastic toy maker. Okay? So over the years which he spent in his career, he's tried to look at various spin chains, tried to look at various phenomena, quantum magnetism, percolation, randomness, fixed points. Then went into dynamics, looking at quenching problems, how one system can be translated from one Hamiltonian to another. Went into topological phases, which came as he was a faculty here, not some of us who saw this in his PhD. So he learned new things. He discovered new things in this new subjects which are appearing. For example, he discovered the idea of dynamical localization. I will allude to it briefly. And in the last few years, he has already gone into the next big leap. He was thinking about quantum information, he was thinking about quantum batteries, about thermodynamics. Over the years, we collaborated with a fantastic set of people, very eminent researchers in the field, various students who mentored, who themselves are faculty members and researchers in various institutes. Some of the students who are here, and as I'm aware, being a collaborator of him, that most of these collaborations were not professional collaborations, but extremely friendly, personal collaborations. The kinds of topics we worked on can be broadly classified into three categories. Critical phenomena, the idea of out of equilibrium physics, and then entanglement and information. And what I will do is to show you some examples in each of these fields. Okay, and of course, this is an informal talk, so please feel free to interrupt. Any questions, any discussions is most welcome. So what is critical phenomena? Critical phenomena is the idea of phase transitions. The classic example being that of this material called magnetite. What has been plotted is magnetization in the system as a function of temperature. This is a piece of magnet, it otherwise is very benign, it doesn't do much. But as you go on reducing the temperature, it suddenly starts attracting another piece of magnet. Okay? And that's essentially what you're seeing here. The magnetization suddenly grows from something which was zero and to a finite time. This is what you see experimentally. For a quantum theorist, this is a classical magnet. Okay? So what is being seen is what is called the Ising model. An Ising model is the most simple way of thinking about a magnet. You think of spins not as quantum mechanical objects as we all know, but just as classical vectors, pointing in one direction. In fact, I can simplify, they just point in the z direction. They can be plus 1 or minus 1. The Hamiltonian is given by summation over ij. The denominator you see is a sum over all nearest neighbor. So you take a periodic pattern like a lattice, like a set of chairs, and put spins on each of them. And the idea is that the spins on every side couple by this term. This is what is known as a classical Ising model. How do I think about a ferromagnet or a paramagnet or a magnet? The system will lower its energy. Hamiltonian is essentially energy. The system will lower its energy when all spins are oriented in the same direction. Okay, as you can see, both of them either plus 1 or minus 1, the energy will be negative, it will be the largest when all of them are oriented in the same direction. Now assume this is what we call a ferromagnet. As you now increase temperature a bit, your spins will start fluctuating because of the temperature, thermal fluctuations. For example, a fluctuation could be a spin just flipping its sign. As you go on increasing the temperature at some value, all of the spins will start fluctuating randomly, and this is what we would call a paramagnet. The system has no more any magnetization. Okay. This is all what is called a classical phase transition. What would I mean by a quantum phase transition? In a quantum phase transition, I will not like to have temperature to fluctuate the spins. I will just want quantum mechanics to fluctuate the spins. And for this, what Amit Dutta used to be really fond of is with the object called rotors. Okay, so let me introduce the concept of rotors. Rotor is essentially a classical vector. You can think of it as a vector. This vector can be in one dimension. For instance, it will just be a scalar. It will do plus 1 or minus 1. It will be unit length. In two dimensions, it could be a vector moving in xy circle. Is this clear? In three dimensions, it will be a vector moving on a sphere. Alright. So this is what is called a rotor. The length of the rotor is fixed and is supposed to be a constant. So this may look daunting, it's not. So this is the Hamiltonian. Let's ignore the first term. The second term is just like the same kind of term you saw in the classical Ising model. It's saying that the energy is minimized when two vectors are oriented in the same direction. It's a dot product of two vectors sitting on some nearest neighbor cells. Okay. The first term is the term which will give you quantum fluctuations. Okay. For example, this is like the momentum. This is position, this is momentum. They are canonical objects. Another way of seeing this, it is a vector in two dimensions. This is an angular momentum which is trying to rotate the spin in two dimensions. Okay. So this will give you quantum fluctuations. So for example, you can take G to be 0. If the quantum fluctuations are 0, all spins are oriented in one direction. And this is again the ferromagnet which we also saw classically. However, when J is equal to 0 and G is large, the spins are trying to fluctuate continuously. Okay, that is what lowers its energy. It's like saying particle in free space will try to delocalize rather than sitting at one point. Okay. And that's essentially saying that this is a paramagnet now, but not a classical paramagnet coming out of classical fluctuations because of temperature, but because of quantum fluctuations. So again, you get a phase transition here, going from as you tune, you set up a value of J, you start increasing G, you start from a quantum ferromagnet to a quantum paramagnet. And that's the kind of phase transition one will be looking at. What Amit Dutta was doing in early of his PhD work was trying to reduce frustration in the system. So let me introduce his first toy model, the Hamiltonian first study. This is work with JKB, who is going to be here very soon, and Professor Vikas Chakraborty, who was his PhD advisor. So if I put J, so he took again a 1D chain of rotors. There is nearest neighbor coupling and next nearest neighbor coupling. Let's put this J2 to be 0. If only nearest neighbor coupling exists with ferromagnetic interactions, we have the same model we just discussed. Okay. So he tried to parameterize the system with the parameter P. If J2 is 0, my P is equal to 1. If I increase the strength of quantum fluctuations, my system will go from a ferromagnet to quantum disordered or a paramagnet. Okay. This is the same transition we just discussed. But now we introduce a parameter called J2. This parameter is trying to align the spins anti-ferromagnetic because J2 is positive. Okay. Since J2 is positive, now the system will lower its energy when vectors are oriented anti-paramagnetic. This is what is called frustration because you don't know what to do. Okay, the spins don't know what to do, whether to align ferromagnetically or anti-ferromagnetically, because these two terms are trying to compete. So when J2 is very large, or therefore this P parameter becomes negative, what they discovered is that the system tries to form a spiral phase. Instead of trying to become a ferromagnet or an anti-ferromagnet, it chooses a particular vector and that minimizes its energy. Amit Dutta in his PhD work found this phase diagram, tried to do a field theory in what is called a large M limit. M is the number of directions in space the spin can take, and tried to find out this phase diagram. So you can see there is a ferromagnetic phase, there is a spiral phase, and there is what yes.
So when you are saying number of direction this can take, you are talking about number of dimension or in
the spin space. So you can think of it this way. This is something which we quite often do, and it's also real. You take a one-dimensional lattice, okay, which is in real space one-dimensional, but the spin which is sitting on every side can live in 3 dimensions.
Yeah. So
for example.
So you are taking that dimension to.
So we are taking the spin dimension, the dimension in which the spin lives, that to be infinite. Okay. So this is a particular limit where a lot of field theory calculations become very simple. It's like a mean field done at what is called large M. The number of directions the spin can take, you take that limit to be infinity, fixing the spatial dimension.
And what happens in that helical?
So this later on actually turns out that there are versions of this where this phase becomes what is called a bond ordered phase. But at that point of time, this was known. This was not known. So this was actually, I think, what they were trying to say is the first order transition from a ferromagnet to the helical phase. Later on, we know at least in 1D and for such systems, this becomes a decayed transition.
So this helical phase would be something like domain balls.
It will be like spins oriented in some direction and will form an overall momentum vector, overall pattern in 1D. Are there any more questions? Okay. He went into then studying what are called long range models. This is again a rotor chain, but here instead of just nearest neighbor or next nearest neighbor couplings, he was putting long range couplings. All spins talk to everything else. However, the strength of the coupling goes on falling as a function of power dipole. And what they discovered here again, that there is a general phase diagram. These are field theory calculations, not there are this is very early on, so you can see that 19, so a lot of numerical techniques which we know now they were not at that frontier, but these became the primary way of analyzing these problems. What they discovered was actually even in one dimension there is a phase transition here, and that phase transition, so this Q, the gamma parameter you see, is like the parameter G, the quantum fluctuations parameter, and this is the classical temperature. So you are going between the quantum transition and the classical transition. He found that even in one dimension you get something called a BKT transition. The BKT transition is known to be a phase transition in two dimensions, or spins living in two dimensions, classical phase transition. This people had not expected that they will be in one dimension, and this is something which they had discovered.
So here the critical value of G has the same connotation as being proportional to J, the interaction in the system.
No, so here, J will be something which doesn't give any fluctuations. J is trying to minimize the
At
energy.
some point, the critical value where the transition sort of
Right.
starts, that is the point at
That-
which
yeah.
G becomes
Order.
J.
Absolutely.
And what drives these quantum fluctuations? These are just like 0-point fluctuations or something?
Yeah, this is the idea that you have 0-point fluctuations of the spins. Absolutely. Okay, and so what they discovered is that there is a two-dimensional transition possible in a one-dimensional Hamiltonian, and this is what is called the BKT transition. And this was done in very early 2000s. Over the next few years, actually, he continued during his postdoc years. He went on working on various rotor chain Hamiltonian. This becomes actually his bedrock. Okay, this idea of low-dimensional phase transitions and spin chains become a recurrent theme in all of his works, and because it was all field theory and extremely hard kind of calculations, that becomes the bedrock on which all of his future works actually rests. So this is a rotor chain with random magnetic fields. So instead of a phase transition done by a uniform magnetic field, you can think that I am going to put random magnetic fields at every site, although the mean of that randomness is 0. And turns out that kind of a transition is again a very different and very interesting phase transition. It is something called randomness fixed points.
Even without the external field, this is the external field.
Is an external field.
But even without the external field, there would be effective field seen by every spin when we invoke this long range.
Yes, that is in this case.
That is already there in that.
In that limit. This is a different problem. What he is doing, you are taking a spin chain which is with nearest stable interactions, but putting magnetic field randomly at every position. And the field strength at that every site is different, but on an average it's 0. And then the question is that can you still get a transition in the system? The mean field is 0, but randomly every site has 1.
And this transition is as a function of like increasing randomness strength.
Increasing randomness strength. You think of a Gaussian, and increase the width of the Gaussian, and at some point it transits to a.
And is there any kind of like localization to this?
So this becomes in fact a precursor to the kind of localization and MDL physics which you use. So here also in fact you get like a paramagnet in some sense. It's frozen. Okay. So then what it starts doing, you take this 1D chain with long range couplings we just discussed, and then say randomly I will remove some couplings and not remove some couplings. And this becomes a problem of percolation on this 1D chain. And this again has a very interesting connection with randomness fixed points. But I will not get into all this, and I will move to the next one. Okay? Let's look at the next part, which is non-equilibrium physics. By about 2005 or so, I think the first time starts thinking about non-equilibrium problems in a very serious way. The idea of quenching he introduces, many of his papers start discussing ideas of quenching. The quenching is that you take a Hamiltonian, any Hamiltonian, and take it to another Hamiltonian, say H2, which means that changing some parameter in the system. Now, of course, if I do it very slowly, then we have the conventional phase transitions as we all know. Okay, so that's like I can change the temperature, I can change the magnetic field, I can change pressure. I will do it very slowly, but system will undergo a phase transition, as we all know. But then what he was asking, what happens if you do it in a finite time? Don't do this extremely slowly. You will start doing it a bit fast. Okay? This is the idea of quenching, that there is a time scale involved by going from one Hamiltonian to the other, and can you find something new? This is the work of Uma Divakaran. I think she was his PhD student here, first PhD student. So they start looking at this Hamiltonian, again a spin chain, quantum spin chain. It has a lot of parameters. You can see that this is the usual kind of coupling, J sigma dot sigma. There is no ZZ, but essentially sigma dot sigma. It's like two vectors dotted together. This is an anisotropic term. This is some sort of a magnetic field. You can see switching sign between +1 and -1 as you are changing the sign. This is a 1D chain. The phase diagram is extremely rich. There is a paramagnet, there is a ferromagnet. There is something called a dimer phase. In a dimer phase, what happens? That spins form singlets, but then the singlets arrange in a periodic pattern. This is a dimer phase. And the question he was asking, that let's quench, say from starting from this dimer phase to this dimer phase. If I do this in a fast time scale, do I get something new in this dimer phase? And what they were able to find, that in fact in this dimer phase you start getting some excitation, what is called some defects, and this defects has some finite density. Some domain walls will remain and they will not go away. It's like you are starting to changing one phase to the other, but some defects get originated if you do it very fast, and those defects have a particular form. The density of those defects goes as 1 by tau to the power 1/3, and this is something they could test numerically and also prove. So the faster we quench, more number of defects we create. If we do it very slowly, then of course there are no defects, and I just go into a conventional phase quench. Amit Dutta studied over the next few years these ideas of quenching and a host of models. This includes topological toy models, for example, Kitaev model, Majorana chains. Of course, I am not going to imagine that I can introduce topological phases here, but just as a primer, it's kind of an insulator, but with some boundary modes and states. He started looking at quench protocols, but doing it periodically, continuously. So you just don't quench it once, you quench it again and again between two Hamiltonians. And what can happen is something called dynamical localization. For instance, you can take graphene or you can take a system which is conducting. You go on quenching it, the electrons just don't move, they just stay there. And you get a new kind of localization, not because of disorder, but because of periodically driving the system. So what he was trying to see, what he was finding, that there are new phases of matter which you will not expect in a system, but you can just get dynamically. You can get because of periodically perturbing the system. And this is where he started posing this question. Just like there are phase transitions in an equilibrium system, are there phase transitions in the dynamical problem, in a non-equilibrium problem? Can I define phase transitions? And to define phase transitions, what I want is something which is a free energy equivalent of equilibrium phase transition. Just like in equilibrium physics, we think of free energies and think of phase transitions of free energies. Can I think of phase transitions in a non-equilibrium? He goes into the theme of dot split overlap or dot split echo. Again, a recurring concept in many of his papers. I will introduce the idea very simply. Again, think of this toy model. This is again it's kind of an Ising Hamiltonian, as you can see here. Two spins are coupled with a ferromagnetic coupling, and this H is trying to give you quantum fluctuations. Okay. You start from some state, but now evolve it with a different Hamiltonian, not with the Hamiltonian. Of course, if you evolve it with the Hamiltonian here, then it will be an eigenstate, it will not do much. But you start with a different Hamiltonian, and now they overlap with this state. So what did you do? You took a state. It is as if you created a different state, applied a different Hamiltonian to it now, and let it evolve. Now ask how much did that state change? This is what this overlap will tell you. If this overlap goes to 0, it's like saying that the two wave functions are orthogonal. The system has started from a phase, but has moved into something which you can't recognize anymore because these two wave functions overlap as what you see. And this object, this overlap, can be thought of as a free energy equivalent. So you can think of this iota T as some sort of a effective temperature. This is called complexifying temperature. Okay. And if you complexify the temperature, log of this object, this is like the partition function, log of this object gives you free energy. And when this quantity goes to 0, my f of z, this goes to infinity. This shows you divergence, which is the idea that the system undergoes a dynamical phase. And he started looking at these concepts in a various systems. One of his work with Victor Shardha, again some of his PhD students here, which shows in a complex plane where temperature and this real time both are there, you get what are called Fisher zeros. This is a generalization of phase transitions in both real time and imaginary.
Actually, HZ doesn't diverge because you are normalizing with the
edge.
symbol. It becomes a non-analytic.
It shows you non-analytic. So over the next few years, he went on thinking about.
Z is somewhat like equivalent of a free energy type of concept.
This is equivalent of free energy. So it will show you non-analytic behaviors. So if you scale it, for showing the same. If you scale the system size, if you increase the system size, more and more it will diverge. So if you scale with this, it will show you non-analytic behavior.
So this final state you are talking about, that is a non-equilibrium steady state? That is evolving, still evolving, or that is?
No, this is, you are doing this as a function of time. That every value of time you are taking,
So that-
how much has it changed?
So you see this non-analyticity of this free energy for any. Okay, sorry. Understood.
Okay. No,
What is the
you can talk to show me later.
Yeah.
What is the RT?
This is the real part of the, so you can, if you take this general iota t plus beta, this is like the real part. Okay. So he went on doing this actually to periodically driving the system. For instance, in 1D chains, topological chains, you have edge modes, you can create many more edge modes. You can do this for a two-dimensional phase. This is some of the work of Utso and also Saurabh later on did some of these things. You will get boundary modes in the system and you can create many of them. Okay, like many more, increase the number of boundary modes in the system by periodically driving. Let's go to the third part of the story, which has to do with entanglement and information. So entanglement, of course, we all know in this form. So if you just take two spins, classically it can take 4 states. Two spins can be up, it can be up, down, up, or down, down. But quantum mechanics allows us to superpose the states and give you a singlet. And this singlet, if you do a bipartite entanglement entropy between the first site and the second site, the entanglement entropy will be log 2. It's 1 qubit of information. What we were trying to do, what Amit Dutta was trying to now think, that can this entanglement be used as a resource? Can they be used as markers for phase transitions? Okay. In a quantum many-body system where you have infinite number of spins, is there a way of thinking about entanglement? What does it play a role in the nature of phase transitions? For instance, in this case, in this particular problem, the work of Somnath, what they were trying to do, this is a 1D Kitaev chain. A Kitaev chain is essentially a 1D superconductor field. It's a one-dimensional superconductor with some topological features. He studied this model with and without a path. You take the system and couple it to a path, to leads if you like. And you can ask that its coupling is 0 and say this coupling is finite. And if coupling is 0, then it turns out that the system's entanglement goes on increasing as you increase the size of the system. Plus, it grows ballistically as a function of time. You do a quench protocol here, the system's entanglement grows ballistically. However, if you couple it with a path with some finite kappa, the entanglement starts decaying exponentially. And this is the idea that entanglement and its characters can also tell us whether the system, the crucial physics of the system. For example, when you couple a path, not only is the system losing energy, it is talking to it in multiple ways, it is also exchanging entanglement with it. And that is going away from the bulk of the energy. Okay?
So the
Yeah.
path is bosonic or
In this case, I think still a fermionic path. Yeah. Yes.
Size is infinite, otherwise it would increase the
Yeah, so you go on increasing this size, you study as a function of it. Okay. This is Saurav's work, which is not here. They have started thinking about quantum batteries, quench protocols, where you think of a very toy model again. One spin, two spin, these are one spin here, another spin here, call it H1 and H2. There is some interaction between them called H int, and there is some coupling with a path again. You think of protocols where you say that let these two spins be there, let me quench the interaction Hamiltonian first. Now let me couple this whole system to a path and then remove the interaction Hamiltonian. I am going to ask how much is the heat exchange between the path and the system. So this is thinking about ideas of thermodynamics in microscopic quantum systems. Okay. For example, they were trying to show if QC and QH is the amount of heat which is exchanged from a cold reservoir and a heat reservoir. They were trying to say that if this QC is greater than 0, this is a statement that you are getting more heat from the cold reservoir and throwing it into the hot reservoir. The system is behaving like a refrigerator. So this is the idea of a quantum refrigerator, which they were trying.
So, what is the concept of a battery here? I mean, that part was not.
So they were also trying to do that, can you store energy and then use it later.
Store energy.
So you use this H interaction to first pump energy into the system,
Achha, that stores
and then you couple it to something else and get that energy out of that stored.
I see.
So that's like the idea of quantum.
So somehow this H interaction is that quantum part, this thing which will help to.
Which will help, yeah, absolutely. Then you can ask, how much entanglement did it create in the system between the two spins, and is that playing a role in the amount of energy you have added to the system? And some of these questions was in fact Saurav's major part of Saurav's thesis. So this is in fact we are already very close, 2021, 22. Okay. This is work of Shobik, where you can take dynamical, you can take spin chains again and ask can non-local string order parameters detect parameter phase transition, something which I hope Saurav will be talking about. And then you can do periodic driving and see, I told that initially he looked at you can do periodic driving and create many edge modes. He was now starting to see that if entanglement, bipartite entanglement and its other versions like mutual information and disconnected entanglement probing, it can be used to detect multiple edge modes in the system, and that we use as a marker. Okay, this is something Saikat will be talking about today in the end of the student units. So, in this last 30 minutes, what I have tried to do, of course, what I have tried to just give you is a flavor of the kind of questions Amit Dutta was trying to ask. These are the glimpses of his physics journey. It is probably important to mention a few things about the impact on the field and the Indian ecosystem. While being in Kanpur, he wrote 2 books, at least 2. These are the 2 I am aware of. As you can see that these 2 books are not textbooks, but they act as the basic resource for many of the condensed matter researchers. Many, in fact, even when I have given lectures on spin physics, I have used his book as a textbook, because this acts as an intermediary book between a graduate physics and something which is at the frontier of the research. And Amit Dutta has a way of writing things which is very clear without any jargon, and therefore these books act like an important resource. He was extremely invested in the quantum condensed matter community in India. This is just a way of saying that he wrote recently an article on quantum dynamics research. It is not an unfair statement to say that in India, anybody who has worked even briefly on non-equilibrium physics or non-equilibrium quantum physics has either read Amit Dutta's papers or has collaborated with them, spoken to him in various conferences and events in a very deep way. He also nurtured this community very much. Many PhD students you are all aware of, many of his short-term and long-term, even short-term students who have done masters with him or just a summer project with him have gone on to become physicists in India and abroad. And it is again not an unfair statement to say that they got infected by him initially. That was the first point of infection. So the fact that he was very much invested in the community is also something which we saw in the QMAT which we organized last year. Meaning some of the younger ones were joined and we used to talk to each other that this is not a conference he was doing just because he was asked to do or the event came to us and therefore he was doing it like a formality. Amit Dutta was doing it as if extended family he has nurtured for a long time and he had invited them at his home. This is a community which is therefore very much he was deeply invested in, and therefore you also see that when people come, when Anindam comes yesterday or anybody who comes and goes, they are fond of him in a very deep way because he also invested in them in a very, very deep way. So what I am trying to do is to show you that while Amit Dutta was making this journey through various places, he was doing a physics journey also. And that physics journey was really those of toys. He was playing with toy models continuously. And toy models have something beautiful about them. They are very simple and they are very sweet. They are engaging and enriching in many ways, and they hold a lot of beauty. So this probably is the way of summarizing Amit Dutta's work. Thank you.